Welcome student to this video where we will solve and we will prove some theorem related to image of a function over a subset and also the inverse image. So if we go to the first theorem, we are given that if C1 is subset of another set C2, then the image of C1 will be subset of the image of C2. So if we just try to visualize it with an arrow diagram, that is my set A. Now if we have C2 and inside C2 there is a tiny one which is C1. So we have C1 inside C2 and we map it with F. What we are expecting is that the big set will be mapped into F of C2, and now this tiny one will also mapped here to F of C1. That's the expectation that we have. So we will write a formal proof to this one. Here we have a statement, start with FP, then we get another statement Q, which is we can use any method of a proof to prove P implies Q. And in this example, we will use the direct proof method. Direct proof method. So assume we have a set C1 subset of C2, and we need to show and conclude the following. We need to show F of C1 is subset of C2. Now, if you remember, if we have a subset relation and we want to prove that one set here on the left is subset from a set on the right, we have, again, we can use the three methods of a proof: direct proof, indirect proof, which is contrapositive, or contradiction. In this case, we will use the direct proof. So we will use pick a point method. So let, of course, anything F of C1, this means I'm in the codomain, so anything here we can choose it as Y. So let Y belongs to F of C1. Now we need to do many steps. Hopefully we can show that Y is F of C2. Now what does it mean Y is in F of C1? It means the following. So Y belongs to F of C1. It means Y equal F of X for some X in C1. But again, we know that C1 is part of C2, so the whole statement can be repeated again, the same statement. We can just change it for some X in C2. It's the whole statement, copy paste, except that I know if X is in C1, automatically X in C2. Now, if you look at this statement, this is exactly, it has a meaning, which is YF is an image of something in C2. And that will end up the first proof of this theorem. Okay, so here's, I can just put an arrow here, arrow here. For the second part of this theorem, part number 2, we will do the same thing. We will use direct proof, so we will have to assume D1 is subset of D2, and then we need to take something here and show it is here. So for part 2, we'll do the same thing. We will use the direct method, direct proof method. So assume we have two sets, D1 is subset of D2. Let X belongs to the inverse image of D1. What this will tell me, this one tells me directly that f of x belongs to D1. But I know if anything is in D1, it's automatically in D2. So I can write the same statement once again. And here I just change D1 into D2. And this is because D1 subset of D2. Now, if something f of x in D2, it means x is f inverse of D2. And that's exactly what I want to prove. I take something in f inverse of D1. I end up with many steps to reach that f inverse is in D2. So please have a look at this one. I advise you strongly to pause this video, look at the proof again, read it again, try to reformulate it yourself, try to do it again by yourself, and check if you can recreate the same proof for this one. Now we'll go to the second theorem, which is will deal with what happened in the intersection of the image under the function and the inverse image of the function. Something is happening in the intersection. So again, I would like you to pause this video, try to do it yourself. See what's going on here, try to solve it by yourself, and then play the video and compare your answer with the answer given here. So here we have the proof. So the first one is kind of straightforward. The reason why, because I already have something, subset of something else. Something on the left, some set of something on the right. So what we are going to do is we will choose something, pick a point method. So I will choose y in f of c1 intersection c2. Of course, this has a meaning. The meaning is y equal f of x for some x in c1 intersection c2. Now, this can be translated a little bit more. How we translate it a little bit more? We can rewrite it again as y equal f of x. We continue writing for some x, but this time it will be x1 and in x2. So I know that x is in c1. I know that x is in c2. So how about I break this statement using the AND? One time I write it with c1, another time I write it with c2. So what we get? We'll get that y equal f of x, and here I can write for some x in c1, and then I can write a big and I repeat the same thing, y equal f of x for some x in c2, x in z1 and x in c2. So I just separate them a bit. So what we are going to get here, this means y is in image of c1 and y will be in the image of c2, and now this will translate into y is in the image of the intersection. And that's how we prove the first statement. Of course, the second statement does not hold, and usually if we want to show that something does not hold, we have to bring a counterexample where the intersection will not be in the image of the intersection. So that's what we need to do if we want to bring a counter example. So I'll leave it for you to think about it and write me the example in the comments. Now, if we go to part 2, part 2 is dealing with equality. So just let me write part 2 again here, and let's do it together. F inverse of d1 intersection d2 equal F inverse of d1 intersection F inverse of d2. How do we do it here in this case? How we do it if they are both equal? What we will do is we will take an x here and we'll prove that it is there. This proof, I would like to bring your attention here because I will do it 2 in 1. Usually, we have to divide the proof into that the first one subset of the other subset of the first one. I'm not going to do this. I'm just going to do both at once. So let x in F inverse of d1 intersection d2. That's what I'm going to do. Now this is the same, so I will write it as if and only if, that f of x is in d1 intersection d2, and this is the same if and only if f of x is in d1 and f of x is in d2, which is, again, it is the same as saying that x is in the inverse image of d1. If we look only at this part, those are the same. X is in the inverse image. It means if we take f to the other sides, f of x, we get it in d1. And x is in f inverse of d2. This is just f and only f. X is in f inverse of d1 intersection f inverse of d2. And that's the proof. And we did it 2 steps together using f and only f. Because we take x in the first one, we show that x in the second one. Now, if we take x in the second one, we just have to go back the steps from down to above. And f and only f, it works in all directions. There is no issue going up and down in this question. Next example, we will do the same thing for the union here. So let's see for the union, what can we do for the proof? I'll do 1 again. So I will take y here. This means f and only f, y equal f of x for some x in C1 union C2, which is the same exactly as saying y equal f of x for some x in C1, or, and that's a big issue here when we say or, so I'm having 2 options in C2. What that means? It means y is in f of C1. This is the first option because it is equal f of x for x in C1, or y is f of C2 where x may be in C2. So I'm having 2 options and I'm open-minded to do both options. This is what I will get, and that means that y either in f of C1 union f of C2. Again, we did the steps, 2 steps together. I take something here and I show it is here, and if I do the steps backward, I will take something here and I will show it is here. Next is the union for the inverse image. So let x and f inverse of d1 union d2, which means this is the same as saying f of x is in d1 union d2, which is the same thing as saying f of x is in D1, or f of x is in D2, which is again the same as saying x itself inverse of D1, or x is f inverse of D2, and that is exactly the same as saying x is in the union. D1, f inverse D2, and in the middle. And that's exactly what we need to prove here for this question. So if you have any question, write in the comment. Thank you for watching. We will continue in the next video proving some other results. Thank you.